All right, guys. Now I'm actually here visiting a friend of mine from graduate school. This is Shawna, and she and I used to have so much fun studying OChem in the library. What,
Oh,
every night,
yeah.
huh?
Oh, yeah. I remember those days.
You remember those days?
Yeah.
Yeah, so there were so many reactions. So
Yeah.
yeah, I feel for you guys. I was there once. Yeah, so anyway, we're covering oxidations now. And the first one I want to show you is reminiscent of some of the reactions you've had before. So do you remember having a cyclic intermediate and a couple of the other reactions we did? Well, let me jog your memory because I think you're going to say no. I think it was the Br bromonium ion intermediate and also the mercuric ion that we saw with oxymercuration reduction. Remember mercuric acetate? So along those lines, we also have an oxygen version called an epoxide. So as you can imagine, the ring strain is much greater with a three-membered ring. But this is something that you can actually have. It's sort of, dangerous to have it though, because the oxygen, it's an oxidizing agent. And so often people use this to sterilize things, but you do have to be very careful of it. So I heard a radio story once, I think NPR reported a hospital had been using this to sterilize equipment, but it leaked out and then they had to evacuate the hospital. So anyway, epoxide is around long enough to use it for things like sterilizing equipment, but we also use it to do other reactions to it. So you'll see that in a second. We're going to take an alkene like we have been before. Pretty much all of our reactions right now are starting with alkenes. Now we're going to oxidize it, so we need an oxidizing agent, and that's what proxy acid is for. Now proxy acid is it's like a carboxylic acid, which I know you know what that is, but we have a per, so you've heard of peroxide. It means extra oxygen. So instead of a carboxylic acid, we have an extra oxygen in the carboxylic acid. So that's what a peroxy acid is. Now there are different examples of specific peroxy acids we use. The most common is something called metachloroperoxybenzoic acid. That's MCPBA. So that's what this is. You could see the benzoic acid, but peroxybenzoic acid because of this O. And then the metachloro. And you'll learn what those things mean next quarter. And then we have peroxyacetic acid, which acetic acid, is when our group is methyl. So in any case, you should recognize it as a CO3H group. Okay, so that's what this is right here. That's what's oxidizing. And so basically we're just adding an O to the pi bond. Here's the actual mechanism for that, but you don't need to memorize that. You just sort of need to know what it does. So it puts that oxygen right here. It inserts it right there, so it's adding to that pi bond. So just maybe think of it like doing something like that. All right? So just to simplify it for yourself. In any case, that's one way to make an epoxide. The other way to make an epoxide, it's not as common, but it's something that your textbook mentions as sort of a fun way to bring back reactions you learned before. And so this one is taking a pi bond, and we're doing a hydrohalogenation. So do you guys remember that reaction? That's where you take a bromonium ion, right? So the bromonium ion is formed, and then you have water attacking that. So in this case it's asymmetric, so it can just attack either one of these. I'll just show it here since we have this version right there. And remember, that's opposite side attack, like SN2. So that's why these are opposite side from each other. Now, the different part that you didn't learn before is we add a base in the second step. So if I take this halohydrin and then I use sodium hydroxide, remember it's the hydroxide part that's reactive. What is the acidic hydrogen on this molecule? Do you see it? She's zoning out. I'm forcing her to think on her toes here. All right. I caught you off guard.
That's okay. Do it again.
Yeah, I've got, now you'll pay attention. All right, well, they're zoning out too, so I'm zoning out too. All right.
No, you can't do
Yeah. So with enough hydroxide, you can grab this hydrogen because alcohols and water have about the same pKa. So then we're going to get the deprotonated form. All right, let's do that. So we're just taking this enantiomer, by the way. But you also get the other one, right? So we're going to do that. So now I want to ask you guys, next step says intramolecular Sn. Oh, if you have stuff to do, you can. Oh, is your cat? It's so cute. If you have stuff to do, you don't have to stick here.
No, I'm having fun.
All right, she's having fun.
It's fast. It's going on real fast.
Yeah, it is sort of fast. We've got an intramolecular Sn2 reaction next. Now, here's where you haven't learned how to do an intramolecular reaction very often. So intra means within, and molecular means the molecule. So within the molecule, we're going to have an Sn2 reaction. So can you guys identify what part of the molecule looks nucleophilic and what part of the molecule looks like a leaving group? And do an Sn2 on that. So hopefully you see that this is the nucleophilic part and the leaving group is the bromine. So if we do that, what do we get? Well, actually, this leads right directly to there. So you don't have to fill anything in there. So that is an epoxide. So that's exactly what we made up here, an epoxide. We just did it in a different way with 2 steps. So instead of MCPBA, we did it with step 1, bromine and water, step 2, sodium hydroxide. So it maybe is not as efficient as just a 1-step reaction, but you can use that if you like. It's more expensive, yeah, and lower yield, probably. So before we move on to too many reactions, let's start collecting our oxidations. Our first one is of an alkene with MCPBA or any peroxy acid. We're going to make it into epoxides. If it's chiral, we get the enantiomers. Or we just walk through an example of using some reactions from before, like Br2 in water, followed by sodium hydroxides. It's another way of doing the same thing. Okay guys, so what we want to do with our epoxides is we can do something fancy, which is called dihydroxylation. So let's review this first step. What are the 2 different ways that we can make the epoxide? One is MCPBA, and the other method, if you want, you could say bromine in water, followed by NaOH. It's not as common a method, by the way, but you can do it. Now notice what's happening here is under acidic conditions or under basic conditions, you can get functional group changes. So instead of an epoxide, we will get 2 hydroxyl groups. You might wonder, where is the second oxygen coming from? And you can see that you can either get it from the hydroxide or from the water. So for these reactions, these are typically covered second quarter as well, but the first one is actually in chapter 8, so it is one that we will learn. The second one I'm just showing you to contrast. So that means that if you were to do if you want to start all the way back here at the alkene, then you would first have to do MCPBA, so step 1, and then to get to the dihydroxylated diol. These are called diols. We've named those before. Then we want to say step 2 will be acid workup. So that's the easiest, simplest way to go from here to here. And then some alternatives are you can do this instead of MCPBA, or you can do base and then acid workup instead of acid. But it seems sort of silly here because you have acid anyway. So this is a specific case that will be covered later, next quarter. Now one thing to notice is the diol. What's the stereochemistry of the diol? You can see that it's a trans diol. So this is how to make a trans diol. The mechanism for a trans diol is like this. So we start with the epoxide, and you don't have to know the mechanism for making the epoxide, but once you've made it, now you should know how this works to open up, because this is very similar, again, to Br2, where you made the bromonium ion, or the mercuric ion in the oxymercuration reaction. So first step is, notice that to open up the ring, we have to have acid present. So that's catalyzing the reaction. So I'm going to use a lone pair and attack one of these hydrogens, and then I'm going to have the protonated epoxide. Now what this does is it activates the ring and makes it more reactive so that water is nucleophilic enough to attack. Now remember, in a cyclic intermediate, you've got a group here that's positively charged. That puts positive charges on these carbon centers. And of these two, the pathway for breaking it open here is more stable than the pathway here, because this is sort of like a secondary or tertiary center, right? So 1, 2, 3, this is like a tertiary center, whereas this is secondary. So the more substitution, the more stabilized this positive charge is here. So we're going to have water come in and attack here, leading to a lower energy pathway. That opens it up here. So this is not driven by steric hindrance. It's actually counter to that. It's driven by these positive charges and what brings down the transition state energies. So after that, we've got water right here. This water molecule ends up turning into this, but then you had a hydrogen from the water that later gets deprotonated. So I didn't show that step, but you guys probably know what's going on there from experience. So that's ultimately what's going on. So we get our trans 1, 2 diol, meaning the diol is next door to each other. So now notice, is this Markovnikov or anti-Markovnikov addition of water?
Well,
Yeah, Markovnikov. But you remember that name?
yeah, one has the hydrogen on one and
Yeah.
the other side.
Yeah, exactly.
Trans.
Yep. So it's anti-addition because the epoxide is on one side and water's coming in the opposite side. So that gives us water that's attached Markovnikov. So this is considered Markovnikov addition, just like all the other reactions we had before. Now with the base reaction, it's actually different. So you don't need to memorize this, but under basic conditions, things are driven more by steric hindrance because of the electron clouds. So here, this is going to come in the opposite side. And so with base, we're going to get anti-Markovnikov. Again, you don't have to focus too much on that this quarter. You'll learn more about that next quarter, but just FYI, 2 different pathways depending on acid or base, giving you 2 possibly different products. In our case, they're both OH groups, so you can't really tell the difference. But if you had an alcohol instead, so you might have an R group here, or maybe you'll have an oxygen 18 labeled compound. In any case, they're slightly different. Now one question for you to think about is, why is it important after you treat with base, you want to neutralize this, so you're going to protonate there. And why do we want to make sure the acid is dilute? So I want you to think back to what kind of reactions we had before, where we had a hydroxyl group react with strong acid. Could something else happen here? So maybe just think about that question, and I'll put it in the answer key. Now another reaction that does a dihydroxylation is osmium tetraoxide followed by a sodium hydrogen sulfite in water mixture to reduce the osmium. So osmium is not very common other than in this reaction. So just make note OSO4, and another way to do this is with KMNO4, and you can see the similarity between osmium and this reagent and this reagent. They're strongly oxidizing, and so what this reaction does is it adds the OH groups, but it adds them in a way that's different from what we had before. So do you guys see? Before we were making trans 1,2 diols, and down here we are making cis 1,2 diol. And we have 2 different ways of doing this. One way to think about this reaction is to think about the structure of the reagent. So you see you have an alkene here, and then OSO4 sort of looks like this. So here's my osmium in the center with 4 oxygens around it. And you can see why it's cis, because the oxygens are adding on the same side of the double bond due to their connection to the osmium. Same thing with the potassium permanganate. You've got 4 oxygens on permanganate, and it's very similar to this in that the oxygens will add to the same side of an alkene. So that leads to syn addition. So before we move on, let's go ahead and summarize these reactions. So let's try practicing using these reagents. I want you to predict the product or predict the reagent you need to solve each of these. Okay, the first one's fairly simple because you just have MCPBA, and I know that that makes an epoxide, so I've got that down. The other ones, number 2 is a little tricky. Here I've got a certain epoxide stereoisomer. I have it being wedged. So I know that what I'm looking at is this group here. So that's the same, and what that tells me is that the nucleophile attacked on the other carbon. So I'm thinking of a nucleophile coming in and attacking, breaking that open, and it remains on the top here. So what is it that attacks here? Well, this is an anti-Markovnikov attack. So here would be the Markovnikov attack. Here's the less substituted side. So the reaction that we covered that's anti-Markovnikov is basic conditions. Again, I probably won't emphasize that too much on your exams, but because we'll cover it next quarter. But this is under basic conditions. So the reagent you need for this one is NaOH, followed by a dilute acid workup. Or sometimes people just use water as a workup. For number 3, so that means that the source of this OH is actually from our hydroxide. For number 3, this is cold KMnO4, and I'm picturing permanganate like this, right? It had the 4 oxygens. So I know it's adding to the same side for the alkene. So that means I'm going to make the OH groups on the same side. So this is a syn addition or a cis 1,2-diol. And that's this reaction we just did right here. And then the last one is another epoxide ring opening, but this time it's in acidic conditions. And then just to change things up, I added alcohol instead of water. So in this case, I'm going to think about the first step, which was protonation of the epoxide to activate it for ring opening. So this is going to grab the H+, and then that's going to become protonated. And then after that, I'm going to think about where I'm going to attack. Now, the nucleophile at this point is going to be my methanol instead of water. So thinking back to what I had before, I had water attacking, and this was a Markovnikov addition. So I attacked the more substituted carbon. So instead of water, I have methanol, and I'm going to attack the more substituted carbon. So that releases my epoxide at the top. Now I'm doing what's called a Haworth projection, which you'll learn more about in OChem 3. But basically it's a side view. So I've got this molecule like that. So side view means that I can draw things on top of the ring and below the ring, and it should be pretty clear. So right here is this epoxide that opened up right there. And now my methanol came in opposite side of the epoxide. So that methanol is going to be hanging down here. Now where does that put this methyl group? Turns out that the methyl gets pushed up to the top. So I'm going to have a methyl group up here. So I've got an OH group here, a methyl group here, and my protonated alcohol from the solvent right here. And then you guys know we have to neutralize that, right? So I'm just going to take another methanol and neutralize it. Here's my final product. All right, guys, so let's summarize that before we move on. Okay, so before we talked about how to make the epoxide. What we just talked about was how to open it up. Okay, so to open it up, we can use acid or base. And if we use acid or base, we have basically water or hydroxide coming in from the opposite side and attacking this epoxide. Now I'm going to just show it as a simple one. Since we're not focusing too much on the stereochemistry right now, let's say we have either acid or base. And then that gives us our trans 1,2-diol. And this is anti-Markovnikov when done with base, or Markovnikov when done with acid. But for now, let's just say we're going to get enantiomers. So if you want the trans diol, you want to go through the epoxide. So sometimes you may have to start with the alkene and make the epoxide and then open it up as a second step. So just consider that. Maybe to summarize all that, basically you are doing this. Step 1, MCPBA. You're making the epoxide. And then the simplest way to do this would just say, acid, and we open it up. Right. So there's sort of a summary of what we did above here combined. All right. The other thing we learned was, what if we don't want a trans 1,2-diol? Then we want to do a different reaction. In this case, we want a syn-diol or cis-diol. And if that's the case, we want to use different reagents. So there's two choices. One is osmium tetraoxide followed by sodium bisulfite workup. Or your other option is you can use cold and basic KMNO4. Now sometimes you'll just see this abbreviated as OSO4 without this step, but it's implied. And then sometimes you'll just see cold KMNO4. But the sodium hydroxide is implied.
Is that weak? That's why I have to be cold, and it'll take longer to do this one.
Right.
Probably faster.
Yeah, OSO4 might be faster. Or cold KMNO4 could be fast, but just to keep it from oxidative cleavage, it's a different reaction. It's the one where you cut through the double bond. Remember that one? That one's coming up next. You might like that one. All right, so now we're going to cover a few more oxidations, but this time with alcohols. So notice we've been making OH groups. Now let's see what happens if we reverse it. We've got an alcohol here, and then it gets oxidized to an aldehyde, and then that can get oxidized to carboxylic acid. So let's write in the functional groups. Now, I took some wine classes at South Seattle Community College on how to make wine. It's really interesting. And I'm here in Davis, California, where UC Davis has quite a wine program as well. And one of the things in their chemistry of wine classes is really understanding this oxidation sequence, because you have wine, which is alcohol created from yeast and acting on the sugars in grapes. And then some of that gets oxidized to aldehydes. And it turns out some of those aldehydes are what create flavors, but also give people headaches. And then that can get oxidized to carboxylic acids. And then that through vinegar. So rice or wine vinegar, right, is from the alcohol from wine getting oxidized. And maybe if you have old wine in your fridge or out, that it tastes really bad or really acidic. So that's what's happening there. So the reactions I'd like you to know are that alcohols get oxidized to aldehydes and carboxylic acids if they're primary alcohols. And what I mean by that is an OH group attached to carbon, which has one carbon attached. That makes this a primary alcohol. So with a primary alcohol, you have the CH bond that's in the aldehyde, but can be oxidized to a carboxylic acid. So you have options there to go all the way or just partially. If you go all the way, you've got this strong reagent, oxidizing reagents, such as Jones reagent, or in other words, these dichromate or chromium-based reagents. So you have sodium dichromate in acid or chromium trioxide in acid, or sometimes we just say Jones reagent. So any of those are fine, as well as KMNO4. Now I put hot KMNO4, but I just meant KMNO4. If you have KMNO4, that's also strongly oxidizing, and you will go all the way to the carboxylic acid with either of these reagents here. But let's say you want to stop it at the aldehyde. Then there's another chromium-based reagent, pyridinium chlorochromate, but it's more mild than the other reagents, so it can only take you to the aldehyde. It won't go all the way. So let's summarize these reactions, and then let's come back and practice those here. All right, so this is different from before because we're starting with alcohols. So this is oxidation of alcohols. So if you have a primary alcohol, you can go to an aldehyde, and then that can go to a carboxylic acid. And so what I'd like you to know is that if you want to stop it at the aldehyde, go ahead and just use the acronym PCC for pyridinium chlorochromate. But if you want to go all the way to the fully oxidized carboxylic acid, you want to use a stronger oxidizing agent. So you want to use either these chromium-based reagents, which you could simply call Jones reagent. And sometimes on standardized exams like the MCAT, you'll actually see these instead of Jones, but we tend to just write Jones sometimes, just it's easier. Or you can write KMNO4. That's a very strong oxidizing reagent, which you saw before. If we see a secondary alcohol, then you don't have the option of aldehydes and carboxylic acids. Let's see what's going on here. With a secondary alcohol, you have carbons here instead of a hydrogen that's susceptible for oxidation. So the best you can do with oxidizing this is to get to a ketone. So in that case, you can use any of these reagents to oxidize from there to here. So we don't usually make a distinction. I think most people would probably use Jones or KMNO4 here. But in some cases, I've also seen PCC used. So any of those options is fine here because you don't have the CH bond that is vulnerable to oxidation as it is here. And then I want to ask you guys a question, which is to think about a tertiary alcohol. If you have a tertiary alcohol, how do we oxidize that? What would we get if we oxidize this? Yeah, why can't we?
I just remember we can't.
Right, you can't, right? Because we would have something like that. And you guys see what's wrong with that? That's what I've heard referred to as Texas carbon. You know why?
I didn't know that.
Because usually, because in Texas, 4 bonds just ain't enough.
Oh, that's great.
Yeah, I know.
I've never heard that one.
I know, that's funny.
That's
I learned that from a friend who teaches chemistry in Texas.
I think
Thanks, Justin, if you're out there. It's a good joke. All right, so now that you've heard all that, let's try to figure out what would you get if you oxidize these alcohols with these reagents. Go ahead and please keep in mind, do we get an aldehyde, a ketone, or a carboxylic acid, or no reaction? Go ahead and give that a try and pause it and come back. All right, guys, so what I do is I usually write out the skeleton of this, and then I know my O is here, and to oxidize it, I'm just going to add the double bond O. So that makes it really simple. But when I have a primary alcohol, then I have to be careful because when I oxidize this, I get an aldehyde, and then I have to check and see, is the aldehyde going to get oxidized? And we know with PCC it's mild, so we keep it at the aldehyde. So I'm just going to keep this as an aldehyde. Right here, KMNO4 with an alcohol is just going to oxidize that alcohol. So I'm going to add a pi bond. And then there's no option for aldehyde or carboxylic acid. This is a secondary alcohol. And my last one is Jones reagent on this guy. So I'm going to start with this and then I'm going to add a pi bond there. And notice I have an aldehyde. So I need to look back and see, is this strong or mild? And this is a strong reagent. So I'm going to oxidize it all the way. Okay, now we're at the very last reaction of the quarter. Woohoo, high five. Last one, you did it, guys. Okay, this one, I love this reaction. Okay, now in grad school, I did one of these reactions. I have to tell Shawna about it, tell you as well. This is a really cool reaction called ozonolysis. And how this works is notice that this molecule with 4 carbons is getting split in half. So it's sort of like that magician trick where you split the guy in half, right? So the way this works is that you have strong oxidizing agents cleave through an alkene, and that's another way of getting ketones and carboxylic acids and things. So what's going on here is we're inserting oxygen where we cleave. So picture that this double bond is actually right here, and then where we broke it, we just stick an O right in there. And then in a different color, I'll show you the other half. The other half we have right here. So that's this guy, and then we just stuck an oxygen right on there. Okay, so we're doing that, and do you see the difference between this pathway and this pathway in terms of the products? So if you look, we have an aldehyde or two aldehydes here, but down here we have OH groups. So that means that one of these is more mild and the other one's stronger. So can you guys figure that out? So with the aldehydes, we're going to have a more mild reaction with the ozone followed by DMS or zinc in water. DMS is dimethyl sulfide. These are reducing agents. So it reduces or keeps it at the aldehyde rather than oxidizing fully. Here we have the full oxidation all the way to the carboxylic acid, and that's because we're using strongly oxidizing conditions like hot KMNO4. Sometimes instead of the word hot, we see a delta symbol meaning heat. And then this is followed by acid workup because we need to protonate these carboxylic acids to neutralize them. So in these reactions, you're doing a cleavage. Now, I used to have people laugh when they heard the word cleavage, immature kids, but I used to laugh too. But anyway, this reaction is really fun though. The story I wanted to tell was that one time I was in the lab and we were doing ozonolysis, but we don't have an ozonizer in our lab. So I went to Dr. Engel's lab and used the ozonizer, and it was really cool because the way that you know that the reaction's complete, you can smell it, but we do it in the hood because it's very bad for you to breathe. In fact, you guys probably know about the ozone layer. The ozone layer, which is really important for protecting us from the sun. And you probably know about the ozone hole, the hole in the ozone layer, which I think in the 80s when we were growing up, we were causing that hole by using hairspray, Aquanet. Sorry, kids. It was our fault. So those aerosols contain CFCs, or chlorofluorocarbons. And anyway, that eats through the ozone layer. But
so you could smell it. Yeah.
So yeah, so you can. So ozone is an extra oxygen, and it the way that you could tell the reaction was complete, that you reacted all of your alkenes, is if you had excess ozone. So to tell if you had excess ozone, you could take your piece of your glove and you'd put it over the reaction vial and it would eat through the glove. Can you believe that? Yeah, it was really fun though. I kept like, oh look, maybe another glove and another glove. But and then it was all like reacted.
Don't do this again.
Don't try this at home. All right, so the mechanism for that is here, but this is to satisfy your curiosity. You don't have to memorize that, but I do think it's interesting to see how that works. But in any case, here's something useful for you, which is to just think of it as cleaving through a double bond. So it's pretty amazing, right? Because you've got two bonds there, and it's just like karate chopping right through that. And then you put O's right in here, so you could actually just picture it as an O and an O there. So you get two ketones or two aldehydes or two carboxylic acids or a combination of any of those. So here's an example of that for you guys. You have a double bond right here. Just cleave right through that. What do you get? You get a 1-carbon aldehyde, but it's got an H on it because that's to fulfill its octet. Then you have the other piece become this ketone or aldehyde right here. So now, what if I used KMNO4 instead? Okay, so if I use KMNO4, hot KMNO4, followed by an acid workup, then what I have is the oxidized versions of these. So instead of this aldehyde, I get the carboxylic acid version, and instead of this aldehyde, I get this carboxylic acid. Now here's the thing, this molecule, when it turns into this, is actually carbonic acid, H2CO3. Carbonic acid breaks down into CO2 and water. So instead of putting this molecule down, I put CO2 plus water, and water's in the solution already, so really I just put CO2. So this group got converted to CO2, and then I also have this group become a carboxylic acid if I have strongly oxidizing conditions. Otherwise, just stick with your aldehydes if you have ozonolysis and zinc. So here's an example of that written out with a different alkene. So here I've got this alkene. So to do ozonolysis, you cleave through this bond here. So I've retained this group here, right here, and I just stuck an O right in there. And then this group here is right there, and I've stuck an O onto there. Just capped those ends with oxygen. And notice with ozone and zinc workup, I keep that hydrogen there. So these are aldehydes, and this one is a ketone because it's got two R groups on it already. This bond is susceptible to oxidation if I use KMnO4 instead. So here is the same reaction, but with KMnO4. So then that bond here, which was under reducing conditions, now gets oxidized if I'm using strongly oxidizing conditions. So then I get a carboxylic acid instead of an aldehyde.
Is there a reason that's not green?
Oh, nice, Shawna. This should be green. Very good. Yeah, thank you. All right. So for more practice on cleavage, oxidative cleavage, go ahead and try this. Start with this alkene. See if you can figure out what these products are. Start with this alkene and see if you can figure out what these products are. And I'll give you a hint. I like to do that cleavage. I'd like to just show it, and that helps me figure out what I'm going to make. And then a little hint on the second one, it's actually going to open up to one molecule. Okay, so sort of an intramolecular thing.
Woohoo!
And one more thing.
Oh.
All right, so the answers are on the next page. So you can see ozonolysis, you get the ketone over here and the aldehyde over here. With stronger oxidizing conditions, I get this breaking down into CO2 and water, and then the other half becomes the ketone. For the second one, I had cleavage here. It helps to number the carbons to see what chain you have, but another suggestion I have is just redrawing this in the same way, but just open it up a little bit. And you'll see that you can just cap that with oxygens right here. All right, so if it helps you to just draw it in the same way and put that in, that's fine. Or you can stretch it out, and I think numbering your carbons just to make sure you have the right number is a good idea. So there's my oxygens here. Color coding look okay? And then I take all the aldehyde groups and I oxidize them to carboxylic acids if I have KMnO4 heated with acid workup. So the last thing for you guys is practice, okay? So it's, before we practice though, let's summarize. Okay guys, so let's summarize our last two reactions. So oxidative cleavage, this is sort of a combination of everything because we had alkene, but we have two pathways. We have either ozonolysis or we have hot KMnO4. So ozonolysis is ozone, usually followed by zinc and water, or can be dimethyl sulfide. And then that's going to give you an aldehyde here and an aldehyde here. If you have hot KMnO4, then I'm basically going to oxidize all of these all the way to the carboxylic acid. So I'm going to get this. But hopefully you recognize this is going to break down into CO2 and water. Sparkling water. Yeah, it is sparkling water. But you don't want to drink that water. All right, so for practice, guys, all these reactions are from this unit. So see if you can figure out what are the reagents you need. And notice that there's one multi-stepper for you. If you take this reaction, what do you need to turn it into this? And actually, that's going to be what we do in our very last lesson, which is how do we link all these reactions together so that we can have multiple steps. And so I'll put these answers in the key, and then we'll have one more lesson on multi-step synthesis. And then we're done. All right, high five. Yeah,
We're
good
just
job.
starting.
We just got started. You just got started. Yeah, this is, you think this is tough. Wait till next quarter.
Oh, man. You can do it, guys.